At this moment, a spacecraft weighing 6,065 kilograms is crossing the inner solar system at roughly 22.5 kilometers every second. That is about 81,000 kilometers per hour, fast enough to cross the entire Atlantic Ocean in under 4 minutes. It is called Europa Clipper. It launched on the 14th of October, 2024, from Launch Complex 39A in Florida, and it is traveling 2.9 billion kilometers to reach a moon of Jupiter, where it will spend 4 years attempting to answer whether an ocean buried under ice could support life. The numbers behind it are worth stating plainly. The mission will cost roughly $5.2 billion across its entire lifetime, funded from the United States federal budget, which makes it one of the most expensive robotic missions NASA has ever flown. The spacecraft itself is the largest the agency has ever built for a planetary mission, standing 5 meters tall and spanning 30.5 meters with its solar arrays extended, roughly the length of a basketball court. Of its 6,000 kilograms at launch, 2,750 were propellant, and only 352 kilograms are scientific instruments. Everything else is structure, fuel, power, and armor. This is a flagship mission, which in NASA's language means the highest tier of scientific program the agency runs, the category that produced Voyager, Cassini, and the Hubble Space Telescope. There are only ever a handful of them in flight at once, and each one takes decades to build. It is going to a moon called Europa because underneath its shell of ice, there is an ocean of liquid salt water that may hold twice as much water as every ocean on Earth combined, sitting in the dark, undisturbed for billions of years. But this is not simply a story about a spacecraft going somewhere far away. It is a story about building a machine to survive a place that destroys machines. Jupiter is surrounded by one of the most violent radiation environments in the solar system, and everything we have ever sent near it has been slowly killed by that radiation. Europa Clipper has to fly through it 49 times. And there is one more thing worth knowing before we begin, because it is the most misunderstood fact about this entire mission. Europa Clipper carries 9 scientific instruments, and not a single one of them can detect life. To understand why anyone would build a $5 billion machine to fly into a radiation belt, we have to start with the moon itself. Europa is slightly smaller than our own moon, and from a distance it looks almost featureless. A pale sphere of ice crisscrossed by long reddish-brown cracks. That surface is water ice, frozen at around -160 degrees, and it is among the smoothest surfaces in the solar system. There are almost no craters on it, which tells us something remarkable. A surface without craters is a surface that is being constantly renewed, wiped clean and reformed, because something underneath is still moving. That something is the ocean. The evidence for it came from several directions at once, but the most convincing came from magnetism. When the Galileo spacecraft flew past Europa in the 1990s, it detected a magnetic field around the moon that responded to Jupiter's own enormous field, behaving exactly as a large shell of electrically conductive fluid would behave. Salt water conducts electricity. Ice does not. The measurement pointed to a layer of salty liquid water beneath the crust, and estimates since then have placed that ocean somewhere between 60 and 150 kilometers deep. The reason it stays liquid so far from the Sun is Jupiter itself. Europa orbits the planet every 3.5 days, and it is caught in a gravitational tug-of-war with Jupiter and the neighboring moons. That constant flexing generates friction inside the moon, and friction generates heat. Europa is being kneaded like dough, endlessly, and the warmth of that kneading keeps the ocean from freezing solid. So we have liquid water, We may also have the chemistry, because the reddish stains on the surface appear to be salts and sulfur compounds pushed up from below. And if there is rock at the bottom of that ocean, in contact with the water, there may be hydrothermal vents down there, the same kind of vents that on Earth support entire ecosystems in complete darkness. Water, chemistry, and energy. Those are the three ingredients life is thought to require, and Europa may have all three. And there may be a way for that ocean to reach us without our having to dig for it. Beginning in 2012, astronomers using the Hubble Space Telescope reported signs of water vapor rising above Europa's south polar region, apparent plumes venting hundreds of kilometers into space before falling back to the surface. The detections have been at the very limit of what Hubble can see, and they have not been consistently repeatable, so the question of whether Europa is actively venting remains genuinely open. But the implication is enormous. If material from the ocean is being thrown above the surface, then a spacecraft does not need to land, and it does not need to drill through kilometers of ice. It only needs to fly through the spray. If Europa is that promising, and we have known about it since the 1990s, why did it take until 2024 to launch a mission there? Part of the answer is money and politics. A mission to Europa was proposed, studied, costed, canceled, resurrected, restructured, and defended for the better part of 2 decades before it was finally confirmed. Concepts came and went with different names and different architectures, each one running into the same 2 walls, an enormous price tag, and a destination that seemed to actively resist being visited. The scientists who spent their careers arguing for it watched proposals die repeatedly. That the spacecraft exists at all is the result of a long, stubborn campaign rather than a single decision. But the harder part of the answer is physics, and it comes down to a single word: radiation. Jupiter has a magnetic field roughly 20,000 times stronger than Earth's, and it is enormous, extending millions of kilometers into space. That field captures charged particles from the solar wind and from Jupiter's volcanic moon Io, accelerates them to tremendous speeds, and traps them in vast radiation belts that sweep around the planet. Europa orbits inside those belts. Anything that goes to Europa is bathed in high-energy particles that tear through metal and silicon, breaking apart the delicate structures inside computer chips, one collision at a time. This is not a hypothetical danger. It killed the last spacecraft that studied Europa closely. The Galileo orbiter, which arrived at Jupiter in 1995, suffered repeatedly from radiation damage over its 8 years in the system, and its instruments and electronics degraded steadily until the mission was deliberately ended in 2003. So the engineers faced a genuine dilemma. To study Europa properly, you want to orbit it, spending months circling the moon and mapping every square kilometer. But a spacecraft in orbit around Europa is a spacecraft parked permanently inside the radiation belt, and the estimates were brutal. An orbiter would likely survive only a matter of months before the radiation destroyed it. The solution they arrived at is the reason the mission is called Clipper, and it is the single most elegant decision in the entire project. Europa Clipper will not orbit Europa at all. It will orbit Jupiter in a long, looping path that swings inward for a close pass at the moon roughly every 3 weeks, and then carries the spacecraft back out, away from the worst of the radiation, where it can rest and recover and transmit its data home before diving back in. 49 passes in total, each one a brief raid rather than a permanent stay. Some of those passes will bring it within 25 kilometers of Europa's surface, closer than the cruising altitude of a passenger aircraft above the Earth. Designing a spacecraft for that mission profile meant solving several problems that had no precedent. The first was power. Almost every mission to the outer solar system has been powered by radioisotope thermoelectric generators, which produce electricity from the decay of plutonium. because sunlight becomes desperately weak that far from the sun. At Jupiter's distance, sunlight is about 25 times fainter than it is here. But the Clipper team chose solar power anyway, and that decision is written across the entire shape of the spacecraft. To gather enough energy from that feeble sunlight, the solar arrays had to be enormous. Fully extended, they stretched the spacecraft to more than 30 meters across, roughly the length of a basketball court, which is what makes this the largest spacecraft NASA has ever built for a planetary mission. And it is worth pausing on what all that surface area actually delivers. At Jupiter, those 30 meters of solar panels will generate approximately 600 watts. That is less power than a domestic kettle, and it has to run the flight computers, the heaters, the radio that talks across 600 million kilometers, and 9 scientific instruments. Every watt on that spacecraft is accounted for. The second problem was the electronics, and the answer to that one is a box. Nearly all of Europa Clipper's flight computers and instrument electronics are sealed inside a container the engineers call the vault. Its walls are made of aluminium zinc alloy sheets a little over 9 millimeters thick, and its entire purpose is to absorb radiation before it reaches the circuits inside. The vault is armor. On the 7th of October, 2023, in the clean room at the Jet Propulsion Laboratory in Southern California, engineers sealed it shut. Kendra Short, the mission's deputy flight system manager, called it a major milestone, because closing the vault meant everything that needed to be inside was inside, and the spacecraft was ready to be buttoned up. Bolted to the outside of that vault is a triangular plate of tantalum metal, about 1 millimeter thick and roughly 18 by 28 centimeters. It serves as part of the radiation shielding, but it also carries something else. Engraved on its inward face is a handwritten poem by the United States Poet Laureate Ada Limon, written for this mission. Alongside it are a representation of the Drake equation, the formula that estimates how many communicating civilizations might exist in our galaxy, and more than 2.6 million names submitted by members of the public. A plate of metal designed to stop radiation, carrying a poem and 2.5 million names, on its way to an ocean that has never been touched. By the spring of 2024, the spacecraft was finished. The vault had been sealed for months. It had been shipped to the Kennedy Space Center in Florida to be prepared for an October launch. And then, in May, the mission nearly fell apart. The way it happened is almost accidental. Engineers from the Jet Propulsion Laboratory were at a conference, talking with colleagues who worked on an unrelated classified satellite program. In conversation, those colleagues mentioned that they were having trouble with a particular component, a type of transistor called a MOSFET, supplied by the manufacturer Infineon Technologies. The parts were rated to withstand radiation, and they were failing at far lower doses than they were supposed to. The Clipper engineers recognized the part immediately. The same transistors were on their spacecraft, thousands of them, distributed through the flight electronics, and all of them sealed inside a vault that had been closed the previous October and shipped across the country. The manufacturer had known about the problem and had addressed it, but had not told NASA, largely because the company did not know how the parts were being used. Deborah Woods, a planetary scientist at the MIT Lincoln Laboratory, put it plainly at the time, saying it was fortunate the issue had come up in conversation at a conference at all, and troubling that this was the only way it had surfaced. What followed was one of the tensest periods in the mission's history. NASA assembled what the team called a Tiger Group, a rapidly convened body of specialists to work out exactly how bad the problem was. The engineers could not simply open the spacecraft and look. As Jordan Evans and his colleagues described it afterwards, they had an army of people going over circuit diagrams and running simulations, trying to determine what would happen if the transistors performed below specification. Every circuit had to be traced, every function assessed for what would fail and when. The alternative was almost unthinkable. Opening the main vault would have meant hauling the spacecraft back across the country to the Jet Propulsion Laboratory, dismantling the sealed container, replacing the suspect transistors one by one, resealing it, and then repeating the entire flight qualification test campaign. That process would have cost an enormous amount of money and would almost certainly have pushed the launch past its window. And the window mattered, because the trajectory depended on Mars and Earth being in exactly the right places at the right times. Miss it, and the mission waits years. The analysis concluded that the spacecraft could complete its mission. The transistors would degrade faster than intended, but the team found that the parts partially heal themselves between radiation exposures during the warmer periods when the spacecraft is out beyond the worst of the belts. The flyby architecture, chosen years earlier to protect the spacecraft, turned out to protect it in a way nobody had planned for. The launch stayed on schedule. On the 14th of October 2024, after a brief delay while Hurricane Milton passed over Florida, Europa Clipper left the Earth. There is a small detail in that launch worth noting. The Falcon Heavy that carried it used side boosters that had flown before, on the launch of NASA's Psyche mission to the metal asteroid a year earlier. The same hardware that sent one flagship mission into the asteroid belt turned around and sent the next one toward Jupiter. The route the spacecraft takes is not direct, because a direct route is impossible. Jupiter is too far and the spacecraft is too heavy for any rocket to simply throw it there. Instead, the trajectory borrows energy from the planets. On the 1st of March 2025, Europa Clipper passed Mars, skimming just 884 kilometers above the surface. And here the maneuver did something that sounds like a mistake. It slowed the spacecraft down. Coming in, Europa Clipper was traveling at about 24.5 kilometers per second relative to the Sun. Leaving, it was down to roughly 22.5. Mars did not speed it up at all. It bent the path and shed energy deliberately because the objective was never Mars. The objective was to fall back toward Earth, whose gravity is far stronger and can give far more, and to arrive there at exactly the right moment. Mission Systems engineer Brett Smith at the Jet Propulsion Laboratory described what happens simply, saying the spacecraft comes in very fast, Mars bends its path, and in exchanging a small amount of energy with the planet, it leaves on a course that brings it back past Earth. That return is now imminent. On the 3rd of December 2026, Europa Clipper will sweep past our planet at an altitude of roughly 3,200 kilometers. And this time, it takes rather than gives. Earth's gravity will act as the slingshot that finally throws it outward toward Jupiter. It is also the last time the spacecraft will ever be near us. While it passes, the team will point the magnetometer at the Earth and use our own well-mapped magnetic field to calibrate the instrument, so that 4 years later it can read Europa's correctly. The whole journey covers roughly 2.9 billion kilometers and takes 5.5 years. The arrival date is fixed and precise: the 11th of April, 2030. It has to be exact because the entire tour of the Jupiter system, the whole intricate sequence of 49 flybys, was planned backward from that moment. Europa Clipper carries 9 science instruments, plus a gravity experiment that uses the spacecraft's own radio system, and every one of them was chosen to answer a single question: is Europa habitable? The most important of them may be Reason, an ice-penetrating radar. It transmits radio waves at 2 different frequencies down into the crust, waves that can reach as much as 30 kilometers into the ice. Some of that energy bounces back, weakened, and by measuring the delay, the instrument can build a 3-dimensional picture of the shell, revealing the layers within it, any pockets of liquid water trapped inside, and ultimately where the ice ends and the ocean begins. It is, in effect, a medical scan of a moon. Then there is MASPEX, a mass spectrometer, described as the most capable instrument of its kind ever sent to the outer solar system. During each close pass, it will sample the impossibly thin atmosphere above Europa, and identify what it is made of, molecule by molecule. Alongside it is SUDA, the Surface Dust Analyzer, a gold-plated instrument about the size and shape of a bucket, weighing around 16 kilograms, led by Sasha Kempf of the University of Colorado. Europa has essentially no atmosphere, so micrometeorites strike its surface directly and blast tiny grains of ice and dust up into space. SUDA catches them as the spacecraft flies through, at closing speeds of thousands of kilometers per hour, and analyzes their chemistry. Those grains came from the surface, and the surface may have come from the ocean. It is the closest thing to sampling an alien sea without ever landing. The rest of the payload fills in the picture. The Europa imaging system will photograph the surface in detail. A mapping spectrometer will identify the composition of the ice. A thermal imager will hunt for warm spots that might mark recent activity. An ultraviolet spectrograph will search for water plumes venting into space. And a magnetometer, mounted on a long boom to keep it away from the spacecraft's own electronics, will measure how Europa's magnetic field responds to Jupiter's, which is how we will finally pin down how deep that ocean is and how salty. When the spacecraft reaches Jupiter in April of 2030, it faces one final problem. It is traveling far too fast to be captured, and it does not carry enough fuel to slow itself down with engines alone. So it borrows again. About 12 hours before it fires its main engine, Europa Clipper will pass Ganymede, the largest moon in the solar system, coming within roughly 200 kilometers of its surface. Ganymede's gravity will pull backward on the passing spacecraft and rob it of speed, reducing how much the engine has to do. The same trick that got it out of the inner solar system will be run in reverse to stop it. Then the real work begins. Every 3 weeks or so, the long looping orbit brings the spacecraft sweeping in toward Europa. During each pass, every instrument runs at once, gathering radar profiles and images and dust samples and magnetic readings in a matter of hours. Then the spacecraft climbs back out, away from the radiation, and spends the following weeks transmitting what it collected across 600 million kilometers of empty space. 49 times if the hardware holds. Which brings us back to the fact that is so often misunderstood, in which the mission's own scientists are careful to state directly. Europa Clipper is not a life detection mission. It carries no instrument capable of identifying a living organism. If there is something swimming in that ocean, this spacecraft will not see it. What it will do is answer whether the conditions are right. It will measure how thick the ice is, what chemistry is available, how the ocean interacts with the surface above it and the rock below it, and whether the energy exists to sustain biology. It is not looking for the answer. It is establishing whether the question is worth asking. And if the answer comes back the way many scientists expect, then the mission that follows will be the one that goes down. For now, the spacecraft is out there in the dark, coasting, its arrays open to a sun that is already growing dimmer behind it. In December, it will pass over our heads one final time, close enough that its instruments can be calibrated against the Earth and the Moon. And then it will be gone, on a road that ends in 2030, above an ice sheet nobody has ever touched. And Europa is not the only ocean out there. Saturn has a small moon that is actively spraying its hidden sea into space, where a spacecraft has already flown directly through the plume and tasted it. But that is a story for another day.